Good morning. So today, the past couple years, I've talked a little bit more about like breaking some things with hardware. And this year, I thought I'd go with a little different approach and kind of talk about how to prevent all the crap that I normally do. My background is electrical engineering. I kind of came into InfoSec and computer stuff as a little afterwards. I spent 10 years doing hardware security research. 10 years doing stuff with hardware. I did silicon debug of desktop and server CPUs and chipsets, and then pen testing of desktop and server CPUs. And I also started doing security training with my former employer. I left 4 years ago. I've been doing hardware security training since then. My classes are called Applied Physical Attacks on Embedded Systems, x86 systems, hardware pen testing. So if you ever want to take my training, just let me know. I'll be glad to tell you all about how great it is. What I normally cover in my training is kind of the basics of like, let's plug some wires together and open some hardware up and see what we can break. And it's kind of like going back to the 90s, right? Like with software stuff in the 90s, if you understood security, you could do anything you wanted to any computer pretty much. So let's talk about that in the hardware context. So first, what's a hardware attack? Then a brief rundown of a handful of hardware attacks that I use on a regular basis and others do as well as how much it costs to do them. Then we'll talk about a little bit on the other side, the hardware defenses. What can we do as a designer of a product that is either a hardware product or a software product that is very closely coupled to hardware to kind of prevent these attacks? But let's take those two data sets and kind of cross them and see where is the money best spent, where is the time and effort best spent that we're going to do something that's actually going to improve the quality of the product and actually make it so the hardware hackers have a harder time dealing with it. So for a little bit of background, what is a hardware attack, right? When we're talking about a hack, an attack, something like that, we want to escalate privilege. We want to get something out of this, whether it's firmware, whether it's privilege, whether it's root shells, whatever your currency is, we want to get that. But we want to use a hardware method to get there. So we want to escalate our privilege. We want to use physical access, the fact that we can actually touch the box, open it up, and look at things. That would be a hardware attack. If we can subvert trusted peripherals, so if we could get a malicious USB drive and plug it in and have software that implicitly trusts the USB drive, we're in, right? If we could do the same with a PCI Express device, an SDIO card, a corrupted network adapter, all of these things are ways into a system, and we're going to subvert a piece of hardware and use that as our doorway into the embedded system. Is that noisy? Oh, okay. Silicon logic bugs kind of are the next level of something, right? When you talk about logic bugs in software, you think, oh, well, here's the program flow. I can see where the logic of the programmer was mostly correct, but they ignored a corner case. Well, corner cases exist in hardware as well. The difference is instead of coding in C or Rust or Go or any fancy language, you're coding in Verilog or VHDL. So that's another opportunity to exploit something that would be a hardware attack. And lastly, we have electrical characteristics of signals. When we're talking about the ones and zeros that are on the line, the voltages, the 0 to 5 volts that end up on the line, if we can manipulate those in certain ways at certain speeds at just the right time, we can also affect how the system operates, and that's what I would consider a hardware attack. Lots of times people talk about attacks on embedded systems. When you package up a router and sell it as a hardware product, even though it's running embedded Linux, right? Once you have the ability to modify the software, right, you're privileged. So whatever we can do in this list to give us access to start doing the software stuff is great, because once it's a software problem, it's someone else's problem. I just do the hardware. So some of the common hardware attacks and associated costs. The very basic is we'll go and we'll open up a box, a router, a phone, anything, and we'll see a nice little bunch of pads that are labeled, RX, VCC, TX, and ground. Okay, this is a UART port. So we open up our box, might be already labeled for us, there might be little holes we have to solder to, or it could be a header. But once we connect to that header with a very pricey $5 cable, right, we hook it up, turn it on, see what happens. 9 times out of 10, you go straight to a root shell, right? That's just the state of hardware these days. Most people don't think about the hardware, don't think about physical access, don't think about why someone would ever open up or poke at ports like these inside of a system, so they just don't worry about it. In the past 5 to 10 years, there's actually been quite a change. I did just say 90%. I would say 50% these days. 5 years ago, 90%. 10 years ago, 99.9% of the time you saw these pins, you had a root shell within minutes of your reach. And $5. It's cheap. So Go a step further, and we might have JTAG, two-wire interface, single-wire debug, any one of these like hardware debug ports. And sometimes you're lucky, you get your headers are labeled or identified. There's a couple standard JTAG pinouts you might recognize very quickly. It is more complicated than you are. There's some software infrastructure and some tooling to let you control the target device. But this is an SSD that I bought for taking apart. And I looked at the box of the SSD, and the box of the SSD had a picture of it on there. It was a little mini NGFF, so a tiny little one that goes on a laptop. And right here on the end of the SSD, in the picture on the box, are 8 pins labeled JTAG. It's like, wow, like they even labeled on the box for me. They must have known I was going to buy it. If you want to talk to JTAG, the cheapest way to do it is just get a little, generic FTDI high-speed serial breakout board. This little board has a bunch of pins. You look at the data sheet, it tells you which wires to connect to what. And if you know which pins are your JTAG pins, you wire it up, and in a few minutes or a few hours or days of software configuration, depending on your situation, you have access. You have the ability to debug the processor. You have the ability to look at memory, change the contents of registers, and basically affect the process. You've got your privilege. So sometimes you don't go attacking the system directly, you just want to get the firmware, the contents of the code that's going to be executed. And in this case, we can look at a board, and this is a little Wi-Fi router. On the left side, we have a big chip, that's the CPU and the Wi-Fi chip. Here we have a bunch of pins, that's actually a UART port. Over here we have a small chip with 8 pins on it, and that's a serial EEPROM. It's an 8-pin chip. This one uses a SPI interface, which takes a whopping 4 pins to communicate with. Some of them are I2C, which only takes 2 pins, right? When you've only got 4 pins to deal with, you just grab one of these little clips that cost about $12, and they're designed to clip right onto that chip on the board. You don't have to socket anything. You don't have to desolder anything. And you wire that up to the same $15 board as before, and you should be able to read the flash right off the system. You don't have to, you take it apart, you open it up, you don't have to disassemble the board, you don't have to take the chip off, you don't have to affect the system anyway, but you've got your firmware image, which you can now go and take a peek at and do some analysis of. So next level of complication is, more faster systems, when you only have 4 wires to communicate with all of your storage, it gets kind of slow. So we have parallel flash, which looks more like this, and it's usually a 16 or 8 or 16-bit interface that usually runs a lot faster. There are clips that don't look like this. They're more like a socket that sits on top of these chips so you could read them in place, but they don't really work very well. They're kind of expensive. They break after you use them once. So this is the kind of case where it's just worth the time to take 10 minutes, get a heat gun and desolder this chip, and put it into a universal reader. So this is the universal reader that I use the most. It's made in China. It's about $50. You get an adapter that will hold one of these chips for another $50. And for $100, you're able to dump the firmware off of this system. This is you might see the Doge quality control sticker that says "such pass." If you're into Doge, this is a what's it called? A chip. This is a single board $9 computer, which is a fun toy to play with. It runs Linux. So let's move onward. Like, you'll get a system, and they won't have the label test points. They won't have the label headers, or for some reason you're not sure if the firmware is what you want, or you want to figure out something else to do. So you need to find all these unmarked test points and figure out what they are. The JTAGulator is a pretty neat automated tool that does that. It's got 24 pins. You hook them up to your test points that you find scattered all around. You can see I soldered a whole bunch of wires really messily. And it goes through and it tests every combination of pins looking for JTAG ports, and you can test every combination of pins looking for UART ports. So we take this process of manually finding the right pins and we automate it. So hey, another performance, way to improve the process, automate it, make it easier. It's kind of pricey. It's $160, but you know what? I've saved far more than $160 in my own time using the JTAGulator. Otherwise, I would have to sit there and try up to 360 combinations of pins. It does it automatically. So moving right along, this is a big step. Before we were going to all these things where we just open something up and use the interface that's there for what it's intended for. When we talk about glitching is where we start messing with the electronics. We mess with the timing and the signals and the clocks. You're diving a lot deeper into the hardware. You need to understand a little more about the electronics. So there's some background knowledge and understanding that is involved. There's a great project, that's the Chip Whisperer. That's the Chip Whisperer Lite. It runs about $300. It's a board just larger than a credit card. It's got an FPGA on it that will generate very precise timing edges, so you can pulse reset pins and change clocks on a system so that your instructions that are normally running their normal method, when you get to the right instruction and you want it to fail or not execute properly, or you want a branch to go the wrong way, you can just pulse a signal on the board and perhaps electrically throw the thing in your favor. On the left-hand side, right-hand side, that's an Xbox 360, and what's on that little blue board is the matrix glitch chip. This is a $2, $3 mini FPGA board that goes through and actually glitches the Xbox 360 just at the right time when it's checking to see if the hash on the firmware is matched or passed or failed. And normally, if the hash doesn't match, it won't execute, it'll halt. But if you glitch at the right time, you pull reset at the right time with this little chip, you can get it to run your own custom unsigned firmware, and you've just enabled the ability to run your backup copies of all your games on your Xbox 360. So this is a real attack. People think of this as kind of hard and difficult and foreign. It's not easy. There's math, there's electronics, but it's totally feasible. So like the last couple steps, we'll talk like, this is actually the previous exit, the original Xbox. A tiny little single board was stuck on the bus lines and sniffed actively what was going on this high-speed link at the time, a few hundred megahertz. For $500, you can get a logic analyzer that'll go pretty fast, and it can let you sniff all this stuff, whether you're sniffing your firmware that's being loaded or a key that's being generated and grabbed from a hardware security module. All this data has to go over wires so we can look at them. And then the last thing, the thing that people like to talk about, but like really doesn't come into play all that much, is decapping, right? This is totally within the realm of like a well-funded hobbyist. I said less than $1,000. It could be quite a bit less than that. You're probably spending more on safety equipment than you are on like the nitric acid and other stuff that you might use. Just to decap something and look at it, with a microscope or something, it's pretty feasible. If you actually want to like do something fancy, like have it still work after you've done that, it gets a little more expensive. You can do things like like clear the flash or clear a fuse bit that prevents you from reading out the flash. If you want to get really fancy, $10,000 and up, you can get into the realm of active analysis. That's where you're going to decap it and then solder some wires on there directly to the silicon, and actually watch internal signals on the chip as the chip executes. That's kind of a pretty exciting stuff, but we'll see. It's really not the approach that a lot of people are taking right now. So common hardware defenses. Let's flip the other side, and actually I'm going to jump a couple slides ahead because I decided I want to do these in a backwards order. So what we can do, if we're designing a product, meaning we're designing hardware, or we're designing software and bundling it with hardware, right? Or any of these scenarios where we actually give a customer a piece of hardware, there's a couple things we can do. So let's not document our test points, right? There's really no design overhead to this. When we go back and test these boards, it might be more difficult because we don't have nice labels, but there's really not overhead. It is security through obscurity, but this is going to push an attack from like a $10 attack right up to a $100 to a $300 attack because of the amount of time and effort that's involved. So a tiny thing like this really like increases an order of magnitude the expense of the attack. So disabling JTAG or UART, right? Most systems have a mechanism. And here there's this debug JTAG mode bit that you can set to 1 or 0, enables or disables JTAG. If you use these kind of bits, it means that JTAG is disabled. Whatever mechanism you use to disable JTAG, though, might still be there for someone to re-enable it. It might require you to have a data sheet or have some intense black box reverse engineering to figure out how to re-enable JTAG, but it's possible. There is some design overhead and validation overhead because instead of just going and debugging a platform, you have to re-enable a debug port and then debug it, but it's not a big deal. It complicates a lot of these cheap attacks. On the other hand, permanently disabling it, whether you remove the traces on the board, you set a fuse that can't be unfused, that kind of goes into the high validation overhead range because if you actually need to debug this part, you don't have a way to do that. You've cut yourself off from that. And there's still, sketchy ways where you can like solder wires directly to pins of chips and perhaps it'll still work, but it gets more complicated very quickly and there's a level of skill that's required. If we're talking about an embedded system, you've got code on it. That code is going to be in storage somewhere. If you can encrypt that firmware, It makes things a little bit more complicated. If you can control the firmware update process, it's a little bit more complicated. This is a capture from Binwalk showing the entropy of a firmware image file. And you see right here, it's really high entropy because it's random looking data. It's encrypted. So there is design overhead. There is validation overhead. And for the user and the operational, there's some cost to it from the process of decrypting. But it really does a good job of complicating a lot of the steps, and it actually, the downside is it could actually increase the attack surface because you're adding a layer of encryption and a bunch of code that handles it that could be an issue for you. Another thing you might hear about is active mesh. This is when we're talking about silicon level attacks. We want to put a top layer of metal over our entire chip, and we're going to sense it constantly, figure out what the capacitance of that metal layer is. So if someone tries to cut through that metal layer and poke inside the chip, we'll notice and we'll wipe something. We'll wipe our keys or something like that. So high validation overhead, design overhead, it's kind of expensive. It can prevent decapping attacks sometimes. If you actually are just doing a passive observation, right? You take power away from that chip and you sand off that active mesh, there's really nothing that's going to happen because there's no power to the chip. It's not doing anything. You'll have the opportunity to look underneath that mesh and observe things that may have supposed to be hidden. Using some integrated hardware cryptographic features, storing keys right on the device, you get to the point where suddenly you can make sure that you have one piece of silicon and nothing decrypted leaves that piece of silicon. This is a much stronger position to be in. What you're doing is you're forcing anybody who wants to attack to actually go to the level of a chip level attack. Board level attacks are kind of completely ruled out at this point. It's expensive in terms of development. It's expensive in terms of validation. It does require operational overhead, and it might actually affect users because you can't do something simple like just reflash a new firmware because it might not be matching. Especially in the case if you have some device-specific keying. This would be a situation where you'd have a unique firmware image for each unique device that's encrypted with a key that's stored inside the piece of silicon. It gets very complicated really fast. What's really cool about this, though, is it can prevent Bohr attacks, the break once, repeat everywhere. So you can do a hardware attack on my one device that I bought and figure out a way to get around things and suddenly go and apply it to 100 other devices in the field. If you have unique characteristics of every single device, it kind of works around that. It prevents some of that attack surface. So 2 minutes. So let's go all the way. Oops. So documenting security objectives. I left this one for last. This one is so easy, right? So we look at open wireless. It says assumptions. There is a private network and a public network as encouraged by the default open wireless setup. Anyone with physical access to the router can run any code they want on it, right? This is great, right? If every product actually made a statement like this, it would make things so much easier, right? We are in a situation where we get chips from manufacturers who don't make any security statements. We have OEMs who put these on boards who don't make any security statements. We have vendors who go package these OEM manufactured boards and don't make any security statements. If everybody along the chain made these security statements, we would at least be aware of what's in scope, what's out of scope, what we think we've protected against and what we haven't. It makes a huge difference in how we actually use the devices. So with very little overhead, we can have a significant impact about how the device is used. So if we quickly kind of cross all this data together, excuse me, you see I plotted all the typical, these handful of attacks I picked out on a logarithmic price chart, right? Don't document our test points. That makes the cheap attacks more expensive, right? It's going to cost us $100 because you decided not to just write UART on the pin. That's a pretty good deal. If we disable a debug port, right? If we partially disable it, we just need to figure out how to re-enable it. We can still find those pinouts. But if we permanently disable it, like we've cut off UART and JTAG. We don't have the ability to go and touch those things or interact with the system that way. If we go in the cryptographic route, right? If we just have encrypted firmware that we load into a chip and then decrypt using itself, yeah, so it's encrypted, but what's the key? Where are we storing it? Can we still sniff the encrypted firmware and get the key and decryption routine with it? If we have hardware baked in crypto, it gets a little more complicated. We talk about active mesh. Active mesh is a really expensive thing, and it really protects against a real expensive attack. The thing is, you'll see that this green box is overlapping these two boxes and none of these. If we didn't do any of these and we spent all our time doing active mesh, we wouldn't be protected against the $10 attack, even though we spent a lot of development time and money going for the $100,000 attack. Device-specific keying is kind of an off-topic thing because it doesn't affect any one device. It's going to more affect how we can port the attacks that we might come up with. But if you didn't sense my bias at the very beginning, documenting our expectations changes how every one of these things are affected. If we have a silicon manufacturer that tells us that if someone has physical access, they can run code, we're not going to waste our time with certain other things because we know that it's out of scope. It's not going to work on this chip, so why would we waste our effort and time doing that? So to wrap it up pretty quickly, so what? Document expectations and expect documented expectations. If you're buying a piece of hardware to put into a product, if you're buying a chip to put on a board, know what the manufacturer expects in terms of a threat model for hardware attacks on this device. The other thing is with hardware, the baseline is low. Software, there's no barrier to entry, right? You get a binary file and you make 100 copies of it in case you accidentally modify one. With hardware, you actually have to buy the hardware. With software, you can just download the tools to dissect it and observe it. With hardware, you actually have to spend $10 to get a serial cable. So we're talking about a barrier to entry being like $10 to $100. Going up to $1,000 is a huge increase in that, and it really rules out a lot of people who just have basic hardware skills that are poking at things. And lastly, these exotic solutions that you hear about are useless unless the basics are already covered. This is the same mindset we have with software. If you're dealing with advanced memory corruption, chaining, vulnerability stuff that software people talk about, it sounds all complicated, but when you haven't covered the bases and blocked off some of the more common simple software attacks, what's the point, right? So start with the basics, get the basics done right, and then move on and expand from there. Any questions? No?